Hello everyone, my name is Kim Haynes and I'm a director in the Columns, Consumables, and Lab Automation group at Waters Corporation. I'd like to thank you for joining me today for this webinar where I'm going to talk about tips and tricks for column selection to help you develop robust methods. The outline for our talk today is I'm going to highlight the importance of LC column manufacturing and what that means to your methods. Then we're going to take a deep dive into column attributes and which ones are important for chromatography and what they actually do, specifically looking at base particles and bonded phases. We'll also take a look at high performance surfaces and column hardware. We'll wrap that into a summary and we'll have some time for questions in the end. So first, let's take a look at LC column manufacturing. Specifically, when it comes to the development of a Waters column chemistry, the goal is to produce high quality, innovative, and reproducible materials that ultimately help scientists now and for the lifetime of their methods. We do this by controlling the entire manufacturing process as all of our particles are synthesized in-house, where some companies may rely on the quality of a third-party vendor to supply the materials. The advantage that this gives to scientists is that we control the quality and we understand the science behind the materials that we're creating. This allows us to quickly create chemistries for specific application spaces, as well as drive new innovations and create the types of particles with specific chromatographic attributes to solve challenges. Now I have a question for you. Which of these attributes makes a column reproducible? Is it the sorbents in the particles, the packing of the column itself, or even the engineering of the steel and design behind the column? All aspects of column production are actually important for reproducibility. Some manufacturers don't have the capability or expertise to control all aspects of column manufacture. Some outsource column hardware, or in some cases, even the sorbents used in packing of the column. Simply cobbling together columns from a list of parts limits the actual quality and the end-use reproducibility of the columns because these column assemblies and assemblers may not fully understand and be in control of their manufacturing process. As well, relying on outsourced materials can provide a concern for product availability and shipment delays for the end scientist, which is you, who is relying on these columns to do their work. And these are risks that Waters simply wasn't willing to accept, which is why we actually control all three of these functions with manufacturing the sorbent, packing the columns, even down to engineering the hardware ourselves. So it's having the complete control over manufacturing that allows Waters to develop the column chemistries that we have today, as all of our chemistries are designed purposefully to address customer challenges when it comes to chromatography. In the following slides, I'm going to talk about the attributes of stationary phase, why it's important for chromatography, and what the impact is. I'll focus specifically on the two key parts of the stationary phase, and that's the base particle and the bonded phase. There are many ways a scientist will select a column, and some common practices in selecting a column could be that it's a column that is cited in a compendial method, such as the USP. Maybe you have a favorite column that you use that's worked before. Maybe you select a column from a similar type of application note, or maybe you even try a Google search and just hope for the best. Unfortunately, none of these selection practices really help in predicting how a column chemistry is going to interact with your analytes or how to guide you to success. So the first one I mention is a USP or L classification type column. So if we look here, for example, at the bottom, we see an L classification, and the definition there is an octadecyl silane chemically bonded to a porous or non-porous silica. So that's here in L1 is an L classification for a C18 column. Unfortunately, there are over 600 columns that meet the L1 class criteria. So how would you choose one over another? If we look at a mixture of compounds and a variety of L1 classified columns, you'll see that from vendor A through vendor F for these columns, we see a great variety of selectivities for these peaks. If we look at peak 2, we see peak 2 that's highlighted in red moving around quite a bit. And then as we move on, we see peak 5 and 6 move around quite a bit more. So there's really no way that you can determine how an L1 column would work based on this chromatography. You can't expect that two L1 columns from different vendors will perform the same. So what's important when selecting a column? For both small and large molecules, the keys to any LC column can really be narrowed down to three basic things: the base particle, the bonded phase, and the hardware. The base particle itself can contribute retention, selectivity, peak shape, and efficiency. The bonded phase contributes retention, selectivity, and peak shape, while the column itself, the hardware, and the material of the hardware contributes to the peak shape and the recovery. And we'll explore each one of these in more detail. Let's start off by examining the base particle. There are 5 key attributes to the base particle that can influence chromatography, and understanding how these attributes impact chromatography can help you make better selections for your application. First of all, we have the pore diameter, which influences retention. Larger pores are usually needed for larger molecules. We have the pore volume and the surface area, which impact the overall particle retentivity. We have the particle morphology and composition, which can include fully porous, solid core, and non-porous. We also have the choice of silica particles or hybrid particles, which impact the particle pH stability and selectivity. We have the particle size, which influence the efficiency and scalability of a method. And then we have the particle surface charge or charged surface, which influences or may suppress any secondary interactions, impacting selectivity and peak shape. Many times you can find these specific attributes on the water's certificate of analysis, which are available online with a specific product page and or in the water's marketing collateral that you may find for the columns. So let's start with pore diameter and what pore size is best. Most chromatographic media contains particles that are porous. Column stationary phases can come in a wide range of pore sizes to choose from, so understanding the benefits of pore diameter is important for a given separation. The pore diameter is reported as the average size of the opening in a pore within a given particle. The average pore diameter is tightly controlled during the particle manufacturing and can be dialed in to meet the specific chromatographic challenges of the analyte that you're working with. As a general guideline, you can select the pore size for the range of analyte that you're working with. For small molecules with a low molecular weight, 60 to 130 angstrom pores are a good place to start. As the molecule size increases, you must also increase the pore diameter to allow access to the surface area within the particle. For small proteins and peptides that have a molecular weight range of 3,000 to about 10,000, you need a slightly larger pore diameter. We recommend 125 to 200 angstrom. For proteins and larger analytes over 10,000 molecular weight, we recommend starting with a pore diameter of 300 angstrom or greater. For very large proteins, viruses, vaccines, it can be challenging to get a particle that has a large enough pore volume with the mechanical stability in the particle to work. So we recommend a non-porous particle with an ion exchange retention functionality on it. As I mentioned earlier, the pore diameter is tightly controlled during the particle manufacturing process. There are a wide range of pore diameters across varying particle substrates, or actual base particles. As a rule of thumb, the larger the analyte, the larger the pore diameter is needed to retain and separate the analyte. The scanning electron microscope images here clearly show the difference in the pore diameters for 3 commercially available Waters size exclusion columns. Here you can see the 125 angstrom, 200 angstrom, and 450 angstrom particles. Here we can see the effect of pore diameter for a given separation of a mixture of analytes that vary in size. It's immediately apparent that the protein peaks are sharper with the larger pore size, and that's really not a great surprise. We note that the effect tends to be more pronounced for the larger, later eluting proteins like BSA, enolase, and phosphorylase. Now let's spend some time talking about the volume of the pore and the surface area of the particle. Again, both tightly controlled and quality control tested, as these attributes can indicate how retentive the stationary phase is and how it can be used to compare different stationary phases of equivalent chemistries. I'm going to spend a little bit of time on this slide because it has a concept that's important to understand. The ratio of the surface area to the pore volume is called the phase ratio, and the phase ratio can be used to determine if one column is going to be more or less retentive when compared to another. For reference, the full equation is shown to the right, where the packing density and interstitial porosity, along with the skeletal density of the particle, whether it be silica or hybrid, are factored in. In the chart to the left, we compared 4 different Waters particles and their respective pore volumes and surface area measurements and their calculated phase ratios. And looking at this chart, you can see that you can get more retention from the BEH 95 angstrom and HSS 100 angstrom particles versus the BEH 130 and Cortex 90 angstrom solid core particles. It's also to be noted here that the pore volume and the surface are controlled parameters, and the Cortex solid core particles, even though it has a smaller surface area, the smaller pore volume calculates to an equivalent phase ratio to the BEH 130, indicating that the same bonding, these two phases would have a same retention, which could be surprising to some. Often scientists think that the percent carbon values can be used to indicate how retentive a phase is, and this can be misleading if comparing different column vendors that use different base particles, because that percent carbon really doesn't indicate equivalency at all. And we'll look at an example of that in the next slide. Here we see an example of how phase ratio actually drives retention. There are 3 different base particles, all packed with the same C18 ligand bonding and all having the same end capping. We see in this example that the higher phase ratio HSS particle has more retention, where the BEH 130 angstrom and the Cortex 90 angstrom have similar phase ratios and similar retention. If we look at the percent carbons, you can see that the 15% at the top, 18% in the middle, 7% at the bottom, there's really no correlation that can be drawn with the percent carbon on these columns. Now let's take a look at different particle morphologies and their compositions. Water's columns are packed with one of 3 different particle morphologies: fully porous, superficially porous or solid core, and non-porous. Each morphology has its own benefits to chromatography. Fully porous columns encompass a wide range of pore diameters and pore volumes. They have a higher loading capacity when compared to solid core particles of similar size, and they can consist of either silica or hybrid particle substrates. Superficially porous particles have increased efficiency over fully porous particles of similar size, and they also have a lower back pressure when compared to fully porous particles of similar size. Non-porous particles offer a good separation for very large molecules, and they're used for high throughput ion exchange chromatography. On this slide, you'll find the Waters column brands that utilize the different particle morphologies. They're separated into fully porous, superficially porous or solid core, and non-porous. Shouldn't be a surprise that most of the brands are fully porous particles, as that technology has been around for decades. The most modern brands are highlighted with the orange boxes with attributes that provide increases in reproducibility and performance. Water's particle technologies can be broken down into 4 particles. 2 are hybrid and 2 are silica-based. If we go from left to right, BEH, or bridged ethyl hybrid, is a fully porous particle with unparalleled pH stability and robustness at elevated temperatures. There are many different pore diameters available to address different application needs. CSH, or charged surface hybrid, is a fully porous hybrid particle that has a controlled positive charge, providing improved peak shape with bases at low pH, exceptional loading capacity. It's ideal for LCMS applications that use formic acid as an additive. HSS, or high-strength silica, is a fully porous silica particle that has high retention due to its high phase ratio. This HSS particle is used for water's most exotic bonded phases, such as the PFP and the cyano, for example. The solid core, or superficially porous solid core particle, provides increased efficiency with lower operating back pressures compared to fully porous particles of a similar size. There are 2 pore diameters, the 90 angstrom and the 120 angstrom. The 120 angstrom is available with the T3 chemistry to provide polar retention and 100% aqueous compatibility. You may ask yourself, what's the benefit of a hybrid particle? Waters actually developed hybrid particle technology to help with methods development. In this example, you can see a separation when using 2 different pHs. You can see there's a significant change in retention for the charged analytes. In the top chromatogram at low pH, the acids are unionized and more hydrophobic and are very well retained. The bases are ionized, show poor peak shape, and are less retained. In the bottom chromatogram at high pH, now the acids are ionized, more hydrophilic, and are less retained. The bases are unionized and more retained, and you can see a significant improvement in peak shape. Silica-based particles can't operate at pHs above pH 7 and 8, so you can't use high pH and therefore see these benefits. Moving along on our agenda for important attributes for peak shape, let's talk about particle surface charge. Surface charge needs to be controlled to ensure reproducible chromatography. For older columns manufactured decades ago, silica often contained things like metals that would cause unwanted peak tailing, especially with basic analytes. Over the years, work has led to the development of pure silica or hybrid materials that would help eliminate these issues. Even more modern chemistries are purposefully using charged surfaces to promote beneficial chromatographic attributes to address these challenges. One challenge that scientists saw was unexpected high tailing for basic analytes when using low ionic strength mobile phase additives, such as formic acid, on modern pure silica or even hybrid particles, and that's due to a net zero surface charge. You can see here that for this basic analyte nortriptyline, at analytical mass loads, we're looking here at 1.25, 0.25, and 0.05 microgram, you see this shark fin-like peak shape. You may expect to see something like this during prep chromatography, but again, I'm highlighting this is at analytical mass loads. One solution that Waters invented was the charged surface technology that's used in our CSH particle and also on our Cortex C18+ chemistry. You can see in this example the increased mass load comparison. It's a separation of 11 antidepressants using formic acid mobile phases. The peaks here are much taller and sharper on the C18+ column, which would allow for easier detection at lower concentration levels. This is a great example of that concept of the analysis of bases and basic impurities. Particle size is also important in order to drive chromatographic efficiency. Smaller particles have more efficiency than larger particles, and the more efficient the column, the benefits of speed, sensitivity, and resolution can be achieved. Here's a graph showing the efficiency versus flow rate for both fully porous and solid core columns. As expected, as you decrease the particle size, you significantly increase your efficiency, as well as increasing the optimal flow rate and increasing throughput. The solid core advantage here is also highlighted, as at the very top, we're showing the 1.6 micron Cortex solid core column. It actually has a 40% higher efficiency than the 1.7 micron fully porous column. We can really examine the impact of particle size by keeping the column length the same and looking at the length to particle size ratio. When we compare all four columns, again, keeping the column length the same, all of them are 50 millimeter length. When we compare the particle sizes, we see that the L over dP is much less for the 10 micron column. All of the run times have been kept constant. On the left side, the y-axis was adjusted to make the peak heights appear the same. Note that as the particle size goes down, the resolution value goes up dramatically, as more efficiency equals more resolution. On the right side, the y-axis values are set to the same scale, and this makes the dramatic improvement in peak height and resolution much more easily seen. And finally, in this section, the bonded phases are the true chemical selectors of the phase. They're the key to altering selectivity, which is desired for methods development. Here's a list of the most common bonded phases. C18 is by far the most popular reverse phase bonded chemistry, but you can even tweak that a little bit. With C18 bondings, you can control the coverage to promote specific attributes. For example, a full coverage C18 is good as a general purpose column, while a mid coverage, as we use with our T3, is good to promote polar analyte retention. A C8 is good for retention of strongly hydrophobic compounds. A polar embedded C18 offers a different selectivity with improved peak shape for basic compounds. A phenylhexyl offers a different selectivity, especially for aromatic compounds. A pentafluoropropyl provides a different selectivity, especially for basic compounds. A cyano gives a different selectivity for polar molecules, and an amide used in the helic phase gives a different selectivity for polar basic and polar acid molecules. Here's an overview of the columns that Waters provides, broken out into a few different categories: general purpose, columns for different selectivities, columns for polar analysis, and columns to improve peak shapes. There are some examples where the chemistries can fit into multiple groups, but keep in mind this is a general overview based on the bonded chemistry. So reversed phase general purpose columns, within the bridged ethyl hybrid or BEH category, you have a C18 or high pH stable and the C8 as well. Within the high strength silica, you have a C18 for high retention. Within the cortex or solid core, you have the C18 again and the C8. And within the CSH or charged surface hybrid, we have the C18 for improved peak shape of bases at low pH. With these same four categories, as we move to selectivity, you'll note that we start to introduce things like phenyl, which utilize a pi-pi interaction. For the HSS, we have the PFP and cyano phases. Cortex has the phenylhexyl, again, the pi-pi interactions. And with the charged surface hybrid, we introduce the fluorophenyl and again the phenylhexyl. For polar retention, which is always a hot topic, you have your choice of reverse phase, which is a little bit easier to implement than helic, but helic again is very powerful. Within those four particle platforms again, you have things like a mixed mode column in reverse phase, which is a combination of a C18 and an anion exchanger. Can be used again in reverse phase for retention of polar acids and neutrals. We have the T3, which is working very well in high aqueous mobile phases. There's a C18SB, which stands for selectivity for bases. This is an unend-capped silica column for unique selectivity. There's a cyano, again with a unique selectivity for polar analytes, as well as a T3 within that solid core family. In helic phase, there is a Z-helic, which gives high retention and high pH stability for polar acids, bases, and neutrals. There's also an amide, which is high pH stable, giving a good selectivity for polar acids, bases, and neutrals, and an unbonded bare helic particle. And within the cortex family of solid core, there's also a helic particle. For peak shape improvement, especially for peak shape for bases, there's the Shield RP18. Within the cortex family, there's the C18+, which has that charged surface attribute, as well as the Shield RP18, again, good peak shape for bases. And within the CSH family, all of the CSH family was designed to give very good peak shapes, especially in low ionic strength mobile phases. We've talked a lot about the column attributes and the base particles and the bonded phases. I want to spend a little bit of time talking about the actual column hardware and the surfaces of the column hardware and the importance of paying attention to this attribute in your chromatographic separations. So the real question here that scientists ask is, does the hardware matter? It absolutely does. Most LC column hardware is stainless steel. And the reason for that is that it has excellent pressure tolerance, it's highly reproducible, lending itself very well to the machining process, meaning that you can be very precise with that material. And it can be made in a wide range of dimensions and formats. However, especially with stainless steel, but also with titanium, non-specific absorption can be a real problem. Certain analytes can bind to metal ions, and that leads to poor peak shape and poor analyte recovery. This in turn can lead to longer run times, whereas if you install a brand new column that hasn't been the surface has been fully passivated with analytes, or if you're not using additives to suppress those reactions, it may require extensive conditioning and therefore extensive passivation. So what this means is that if you're analyzing analytes that are acids or phosphates or even sometimes nitrile containing type compounds, it can be unpredictable. These analytes may bind to or chelate, have a chelating type reaction with the metal surface. And again, this can be unpredictable and it's not static. These analytes may bind and then release as well at unpredictable times. So how do scientists address these challenges with the hardware today? This isn't a new problem. This is a problem that's been around for, quite some time. So, some of the solutions include things like passivating surfaces with an acid, and that works by removing the free iron from the steel surface. And typically you do this with a very strong acid. The consequence of that is that it's time consuming. You're dealing with a fairly, again, strong acid, so it's dangerous type solutions, and it's not stable. It needs to be repeated because it wears off over time. Another solution is passivation of surfaces with a sample or matrix, and that works by using that analyte or matrix to essentially coat the reactive surface. The consequence of that is that you're going to spend a lot of extra time, so it's time consuming and again, not stable. It will need to be repeated. There are choices of other materials. So scientists can use things like PEEK or PEEK-lined steel columns. That works by replacing the metal with a non-reactive material. However, PEEK alone is not high pressure tolerant. And if you use things like PEEK-lined steel, those materials tend to have higher dimensional variability, so they can lead to higher RSDs. They have lower frit permeability, and they're also incompatible with some solvents. Another alternate material is titanium. How does it work? As I mentioned, it doesn't. Titanium's also a metal. It will still have non-specific absorption. It can be different than stainless steel, but it still suffers from that. So the result is analyte loss. Another alternative is industrial coatings. So that's, taking some types of materials and trying to, cover up the stainless steel. And depending on what the material is, You may have things like MS bleed or other unexpected problems, and you have to be careful that you're using material that was actually designed for LC and LCMS applications. Another and last example is things like additives in the mobile phase. And these are additives that are intended to chelate with the metals to prevent analyte absorption. Some consequences of that are ion suppression or other unknown effects. You have to continually use them at the specified concentration, and they can present some possible solubility issues. So while none of these, they're all, solutions that people have used over the years, none of these are great solutions to a problem, and there are definitely consequences for each one of these. This challenge of nonspecific absorption was something that was plaguing our own application scientists as much as it was all of our scientists that we work to serve and assist every day. To address this challenge, we invented the max peak high performance surfaces specifically to prevent metal interactions within the separation system as well as the column itself. These are specifically really well suited for reverse phase and hydrophilic interaction chromatography, or HILIC, as well as size exclusion. The first iteration here was to take advantage of the hybrid organic inorganic silica surface. It's very similar to the X-Bridge and BEH hybrid particles. Again, this was purposefully intended for chromatographic separations. You can see here in the diagram, we take the hardware itself and we actually use this resilient, highly cross-linked layer containing the ethylene bridged siloxane groups with the actual hardware. And then we can pack these columns with those precision chemistry particles that we use for these separations, like HSS, BEH, CSH, the Cortex chemistries, and create those separations without the fear of nonspecific absorption impacting our chromatography. Here's a really good example of the impact of max peak high performance surface column technology on a separation. The analytes shown here are adenosine mono, di, and triphosphate. They're all known to bind to stainless steel surfaces. The chromatogram on the bottom was obtained using a conventional stainless steel column packed with the BEH Z-HILIC particles. While the chromatogram on the top, we used the Max Peak Premier hardware with the same exact packing material, that BEH Z-HILIC column. The top chromatogram shows very large improvements in the peak shapes and peak areas, especially for the ATP and the ADP. Now, to keep the system effect out of this, we actually used an Acuity Premier system, which contains max peak high performance surfaces, to ensure that there was no non-specific absorption within the UPLC system itself. So here you really see the impact of the max peak high performance surfaces column technology on the separation. So I've presented you with a lot of information over the last 38 slides or so. So I wanted to give you a summary as to what our more modern small molecule column portfolio actually looks like. It can be confusing. As I mentioned, an L1 column, if you see that in a USP designation, how do you know what column to choose? So let me give you an overview of what that looks like. So here I'm showing you a snapshot of the ever-growing family of selectivity choices of columns based on the hybrid and silica particle compositions that I showed you earlier. And these are both fully porous and solid core particles that are fully scalable to HPLC and UPLC and UHPLC, so that 2.x micron particle space. There are select offerings of columns that can be purchased with the Max Peak High Performance Surfaces technology that I talked about just on the immediate previous slides. So there are 11 hybrid particles. There are 8 based on the BEH particle, 3 based on the CSH or charged surface hybrid particle. There are 12 silica-based particles, comprised of 5 HSS or high-strength silica, 7 Cortex or solid core particles. There's a lot of different selectivity choices that you see here, and all of these that have this Max Peak Premier symbol next to them are available in the Max Peak High Performance Surfaces hardware. And that's meant to eliminate the non-specific absorption and really give you that better peak shape, better sensitivity, better reproducibility, and just eliminate doubt from your chromatographic separations so you just don't have to worry about that interaction. Wow, that was a lot of information. So let's wrap this up into a summary. Understanding columns' attributes, the particle technology, as well as the bonding technology will help guide you to better column selection. For selecting a new column or selecting an equivalent column, it's best to screen columns packed with various base particles and bonded phases if you want to maximize selectivity. And Waters provides a wide range of columns based on hybrid and silica-based particles with varying chemistries, varying ligands to choose from. And remember, those ligands are those chemical selectors that really give you different selectivities and cover that wide selectivity space. Column hardware is something you can't forget about, and it can impact your chromatography. The Waters Max Peak Premier columns are packed in the Max Peak High Performance Surface hardware designed to improve your peak shape, improve your recovery for metal-sensitive analytes by eliminating non-specific absorption that bind to stainless steel.